For those of you who made it to the awards ceremony last night, you'll recall that Simon Brodkin, the comedian, the host last night, actually said, JC who? And once I got down from that moment of embarrassment that you didn't know who we were, I realised that you guys are probably sat there thinking, why are we listening to JCB, a manufacturer of diggers, when we're all on the on-highway market? Well, as I look at the world today, I think we're all facing some very similar challenges. We've got a growing population, which means we need to build more houses, grow more food, move more material for those people. We need more infrastructure to deal with that. We've also got reduced resources, less land, less water, less skilled people, less fuel. And what that's really driving now is an increasing inflation, growing pressures on business to do more with less, to be more efficient. And on top of that, we now have a new drive to be more sustainable than ever before. So hopefully you'll find this speech interesting. Hopefully you can see some value for your business and you can see some similarities in that as well. I rather suspect that there's another similarity with many of your businesses in the fact that they were family businesses. Ours still is privately owned and run. That gives us significant opportunity in these markets. But it also allows us to live to some family values. That jamais content doesn't mean that we're never happy, but it always means that we're looking for a better way. We're trying to innovate. And certainly our 78-year history has been founded on that. We are a very diverse business. We make over 16 different product group ranges. And you'll notice up on the right-hand side, we're also relatively vertically integrated as well, making our own axles, transmissions, engines, and cabs for many of our machines in the range today. I hope you can see that the similarities in the complexity, the range of products you're working with, and that's some of the challenges we all face together. We are a global business, we've got a significant footprint, and that means that anything we do, anything we think about for the future has got to be globally scalable as well. It's not just about this market here in the UK. Now, my role at JCB as General Manager for Product Support, I'm very fortunate to look after our telematics business, and that's where the relationship with Microlise is really founded. For 15 years, really, we've been connecting to machines and using Microlise as a key partner to do that. And it delivers a huge amount of value for our customers, our dealers, and of course for our business ourselves. Today, it's all about connecting us to our customers and to their machines. It's really important that we simplify that process so they can get quantifiable value out of it and use their machines to get the most. We recognise, like many of you operators, that you work with a mixed fleet, so we have to do that in our new system. And of course, everyone wants to be mobile as well. Now, shortly we'll talk about using the right technology for the right application, but the way we work with Microlise is all about the right insight to the right person at the right time to make sure they can take action. We, of course, do everything you'd expect from a telematics system around providing alerts, driving action in their businesses, but also, and increasingly, we're seeing pressure from customers to provide all the information they need with their ESG reporting to make sure that they're delivering on their achievements and their goals and challenges that they've set themselves in their business. Ultimately, we're about being completely connected, helping people make data-driven decisions, be operator-centric as the person who can really change their behaviour, and finally, maintaining maximum uptime. Now, why am I telling you this? LiveLink and telematics is a critical part about our transition to net zero. It's driving behaviour across all areas of our business. Telematics and fleet management has a huge impact on our customers and their operations, on our dealers and the growth of their businesses, on JCB service and our aftermarket, but most importantly, on our engineering. And Tom will talk shortly about our road to net zero and how important technology, how important telematics has been in understanding where those opportunities and where we can drive. So thank you very much for listening to my introduction. I'm going to hand you over to Tom now, who's the real magic as principal engineer behind the hydrogen project, to talk us through how we get there.
Brilliant. Thanks, Tom. Yeah, so as Tom said, we love getting into the detail, we love getting into the data to really understand what our customers do to make sure that we design machines that work for the customers in the future. So I'm going to spend a little bit of time really going through our road to zero, or as at JCB we prefer to call it our off-road to zero. Because we are different, we aren't on-road, we are off-road machines. Our machines are work tools. Ultimately, our industry started with wheelbarrows and shovels, and they just got a little bit bigger. So in terms of our product range, and Tom alluded to the fact of JCB who, so JCB we are a global company, and we make machines everything from 1-ton mini excavators up to 50-ton excavators, dump trucks, wheel loading shovels and tractors. And really to say about this product range is that within this product range, we also have machines that work in urban environments and remote environments. And typically, compact machines work in urban environments, road maintenance, building maintenance, infrastructure, while the large, heavy machines work in remote environments, building the new infrastructure, building the rail links, the road links, the airports, and also growing our food. So when we look at the UK climate change targets, and really this is why we're all here. The graph's gone a little bit skew-if. We're going to try and get to net zero by 2050. And so what you can see here is on the y-axis, we've got UK CO2 output per year. And as you can see, over the past couple of decades, we've been making great progress on that. And really, that's been mainly driven by coal-fired power stations, the move to gas, and then something that we don't really like to talk about, which is the offshoring of manufacturing. Fortunately, it looks good for us in terms of our CO2 footprint, but actually steel, heavy manufacturing is made overseas and contributes to other countries' CO2 footprints. And actually, if we look at this for all other countries, and if you put up India or China onto here, you'd see that graph going the completely opposite way. And then at some point, getting to net zero. So anyway, back in 2019, the government set the target of net zero by 2050. And then more recently in 2021, they set this interim target at 2035 to get a 78% reduction by 2035. And really, how are we going to achieve that as a country? Well, firstly, we're starting off, or the government's starting off with cars and vans, then into heating systems, HGVs and buses toward the end of the decades. Then we get into shipping and aviation and construction and agriculture. And for a long time, really, shipping and aviation and construction and agriculture were considered too hard to decarbonise. So back when they made the Climate Change Act, shipping and aviation and construction and agriculture were considered too hard, too difficult to decarbonise, and therefore were allowed to keep producing CO2 emissions going forwards. Back when they then got to the net zero target, and now we've got to fix this problem. So you might be thinking, well, we're in 2024, why is JCB here talking about our road to zero when you've got until 2050 to solve it? Well, the challenge is that JCB customers have all sorts of products within their fleet. They run cars, they run vans, heating systems, HGVs and buses. They ship things around the world, and obviously they use JCB products as well. So really they're looking for a wholesale CO2 reduction and elimination as quickly as they possibly can for their targets. So what's JCB done to date? And this is really the first sprinkle of where we use our LiveLink telematics information. So on the y-axis, we've got our annual JCB CO2 emissions per machine, and then on the x-axis, we've got time. And what you'll see is that actually over the past 10 years, we've made some fantastic progress in terms of CO2 reduction. So this line here is real data based off LiveLink telematics, which shows exactly what machines do in the field, how much fuel they use, and therefore how much CO2 they produce. So we've made great progress over the past 10 years, and there's a few reasons for that. The first thing was really that back in 2010 and just before, when we knew we were putting telematic systems onto our machines, we realized that our customers were instantly going to know exactly how much fuel they use. And then maybe they'd compare that to our competition. So we realized that actually we want to make sure that JCB products are the best on that graph. So we worked really hard to get our fuel efficiency up and therefore get fuel consumption down. The other reasons for really doing CO2 reduction and fuel consumption reduction at such an early stage was that we need to prepare our machines for future technologies. So if we want to move to batteries or to hydrogen, the density of those technologies means it's difficult to put enough energy on board. Therefore, our machines need to use as little energy as possible to make that work. So over the next decade, we're going to go again on efficiency and try and get another 50% out by 2030, really to enable us to get to future technologies. Now, when we think about our electric machines, if you think back to the JCB product range, and you see that those compact machines, actually, they work in an urban environment, they don't do many hours a day, actually we could electrify them. But if we did electrify all of those products, and we were getting our electricity from renewables, actually we'd only have an effect of about 5 to 7% on JCB's CO2 emissions. And the reason for that is that they don't use very much fuel, therefore they don't produce very much CO2. Actually, it's the larger machines which work longer hours, they use more fuel, and therefore they produce more CO2. So for those larger machines, we need a carbon-free fuel, a fuel that we can take to machines and that allows people to do exactly what they want to do with the machines when they want to do it. So this is probably our most important graph, and it's my final graph, you'll be pleased to hear. So this is a graph of energy demand or fuel consumption on the x-axis, low, medium, and high, and hours on the y-axis, low, medium, and high. And now we've got about 500,000 machines on our LiveLink telematics system. And if we plotted all of our machines around the world onto this graph, the line would look something like this. As you'd expect, machines that don't consume much fuel don't work many hours. Machines that work a lot of hours consume a lot of fuel. But we also like to benchmark other industries, and in some ways that's partly why we're here today, is to learn from other industries about how we can apply technology, how we can decarbonize. And if we put different industries on here, we think they look something like this. Now we consider a car relatively low energy and low hours. And why is that? Well, your car is parked for 97% of the time. Most people do 20 minutes driving in the morning, 20 minutes in the evening to and from work, maybe a bit more at the weekend. But actually, they're only doing about 300 to 500 hours a year. And that's quite similar to a compact mini excavator. They also weigh about 2 tons, just like a mini excavator. As we go up that graph, you then get buses. And buses, and we consider them fairly gentle. They do a repetitive route around towns and cities all day. And again, we'd consider that similar to our telescopic handlers, which go around our building sites, dropping off pallets, moving material all day. As we then get up into the trucks, we think they're more like a backhoe loader. So a truck drives to work, works all day, drives home. That's its job. You know, it's about maximum uptime for the owner and the operator. And a backhoe's the same. A backhoe loader drives to work, does a job, works all day, and then drives back to the depot at the end of the day. And then finally, we've got trains. And really, we consider trains similar to our heavy excavators. They need a lot of power, and they work a lot of hours. I think at the moment, you can get a train from Derby at about 4:30, 5 o'clock in the morning. Then you can get one back in again about 1:30. So actually, in terms of the amount of running time that train is doing, it's only stopping for a change of driver, change of fuel, and a clean. And that's similar to an excavator. Now, if we could actually put a third axis onto this graph, we'd have transient load. Essentially, how quickly do you need power? And this is where a train and an excavator are similar, but also different. So where a train going from here down to London might stop 2 or 3 times on the way, and therefore it stops, and then you've got to go back to full power to really get that heavy mass away from the station and onto its destination. Well, our heavy excavators do that every 27 seconds. So every 27 seconds, the machines go from 0 load in the air to full load ground engagement. They dig through the ground, they turn, they dump, and then 27 seconds later, they're back again. So where the train might stop 6 or 7 times on its route, our machines are doing that every 27 seconds, twice a minute. So we started this decarbonisation journey really with electric. And we thought, well, we'll start small and we'll work our way up. It'll be fairly straightforward, fairly boring, to be honest. As engineers, we're just going to put more and more batteries on, and we'll just work to 2050 and it'll be fine. But what we realised quite quickly when we were talking to our customers is they started talking about a job site limit. And we said, well, what's this job site limit? And he said, it's the point where, number one, the sites don't have electricity today. Number two, as machines get bigger, the amount of batteries they're going to need on board also gets bigger. But as machines get bigger, they're used for more hours a day. So the amount of time you've got to charge goes down. They said, battery electric just won't work for our industry. What we need is a mobile energy source for fast refueling. We take fuel to machines today, and we refuel quickly, allowing them to operate for another shift, whenever they're needed. Battery electric can't do that. Now, saying that, we do have a battery electric range at JCB, and we're very proud of it. And it's important to say, because we're not, I think the danger is that we come to a show like this, we bring our engine, everybody thinks, oh yeah, you just make engines, you just like engines. But actually we started our journey on battery electric. And we are the industry leader on battery electric products now. We've got 22 different models. So we started off with our electric mini excavator, it's just on the left-hand side. It's award-winning. We beat the Jaguar I-Pace to the Royal Academy of Engineers McRobert Award. And really, the reason why the judges said that we won that award is because we put a focus on efficiency. We didn't just throw batteries at the problem. We tried to make the machine as efficient as it possibly could be to put the minimum number of batteries on, therefore make the best commercial offering possible. So we've now just recently launched 2 extra electric products. We've got a electric wheeled loading shovel and an electric access platform. And we've now sold over 20,000 electric machines worldwide. So we are the industry leader, and we're going to keep doing it. But what we find is that customers want to use electric machines for specific applications where it pays. And that's really important. So where we find people using these machines is underground, indoors, working at night, where otherwise you've got to pay for permits or fume extraction systems. Now, and it's really important to stress this, and just in the same, I suppose, with the truck industry as well, that these are capital assets designed to do a job and earn money and either create value or do a job. And they're not vanity items. While I love diggers, actually the people that buy these machines generally are in finance and on Excel and don't ever get outside. Maybe that's an overstatement. So the question really is, do batteries scale? So we've got our electric mini excavator. It's got 20 kilowatt hours worth of batteries on board. It's used intermittently. We've packaged them into packs, so we've got 4 of these packs. The batteries on this machine cost around £8,000. What it does mean is that the machine costs 1.7 times the price. So if the diesel version of this machine is probably £22,000, you're now looking at a machine that's sort of pretty close to £40,000 for the electric version. And it weighs 2 kilograms more. So we've got the advantage on these machines that we have counterweight, so we can take weight off the back and get it to almost balance. But the question really comes, well, what do you do with a larger machine, with a large excavator? So we had a look at this, and as engineers, we can do anything. And so we went away and we analysed and said, right, this is what we can do. So some people work 22 hours a day with these machines, some people work 12. So if we split the difference and say the machine's got to work 16 hours in a day, that machine would need 200 battery packs. The batteries alone on this machine would cost £400,000, which means that the machine would be somewhere pretty close to £600,000, 4.3 times the price. Bear in mind that a diesel version of this machine today probably costs £120,000, £130,000. So it's a big on cost. And the weight of the machine, well, it's not a 20-ton excavator anymore. It's a 30-ton excavator. But it can only do the work of a 20-ton excavator. So, we showed this to our customers and said, is this what you want? Is that suitable to you? And they said, well, on a good day, normally with a diesel machine, for £1 million, you might get 10 20-ton excavators. What you're telling me now is that for £1 million, I can only get 1.5 20-ton excavators. But the person's not going to pay me that much more to do the job, to move the earth. At the end of the day, these are capital assets. They've got to earn their keep. So we said, all right, okay, we can compromise. As good engineers do, we can reduce the weight, reduce the cost, and reduce the charge time. So we can create a machine that only works 4 hours a day. Now, bear in mind that they still need to do the 16 hours worth of work, so they're going to have to work for 4 hours, then put the machine on charge for 3 hours, have a 3-hour lunch break, come back again, do another 4 hours, have a 3-hour dinner break, and come back, do another couple of 4-hour shifts. It's just not feasible. But the batteries on this machine would cost £100,000, so the machine would cost twice the price, maybe that's okay. And the machine only weighs 2.5 tons extra. But the problem is that this isn't designing a product which can do the job properly. So we love to go to all the different trade shows, and we put our jeans and our hoodies on and we pretend like we're machine customers, and we go around all our competition and we talk to them and we learn a lot about what they do. And some of our competitors have done this, and they've taken machines to shows. And what's really interesting is that when you get companies and their own engineers come and talk to each other, they start to share all the secrets. And we've heard stories that by charging these machines 4 times a day, well, obviously you reduce your battery life by 4 times. So if the machine was going to have a 10-year life, now on a battery it's 2.5 years. Some real challenges with this about how you deliver a product to the market properly. I think it's easy for us all, we can all make prototypes that look great but ultimately don't do the job. What's really important is that we listen to our customers, we use the data from LiveLink telematics, and that we deliver products to customers that are exactly right for what our customers want to do with them. So it keeps coming back to the fact that customers demand a mobile fuel, and they demand maximum uptime from their machines. Now, these are real photos of our machines, and you'll see on the right-hand side we've got our JCB backhoe loader. So that machine probably did a day shift, and then at night it then did another shift with a night team. Now, these machines are worked hard, they're worked for long hours in a day. So we then went and said, well, we want a mobile fuel, a potential future fuel. Let's look at all the different fuels. So we looked at HVO, biogas, e-fuels, ammonia, and hydrogen. And really, we settled on hydrogen for one reason, or 4 reasons actually. It's transportable, it can be produced from renewables, it's zero carbon at the tailpipe, and it's non-toxic. The other thing to say, and actually I'll just flick back, of these fuels on here, HVO, e-fuels, and ammonia all require hydrogen to produce them. So actually, a more efficient way is just to use the hydrogen in the first place. So we had hydrogen, we knew we wanted to use it, and so the most obvious technology to use at the time was a hydrogen fuel cell. So back in 2017, 2018, we set about building our first hydrogen fuel cell powered excavator. Unfortunately, we couldn't get a fuel cell that was the right size at the time. Apparently, the fuel cell world was focusing on cars at the time, and so we could only have a small one. So we took it, we put it on the machine, and we supplemented it with a load of batteries. And it worked, but not very well. Fast forward to a few years later, and the fuel cell world were knocking on our door saying, the car thing didn't really work out. We've got a bigger one now for you. Would you like to put it in our excavator? So we knew we'd learned a lot from our first prototypes. We thought, we'll have another go, and we'll try it in our second generation prototype. So this was back in 2019, 2020. So unfortunately, I can't show you a video today of what goes into this machine, but the thing to say is that this machine is the most complicated and most expensive and most technologically advanced machine we've ever built. It was absolutely fantastic as an engineer to be working on it, but the manufacturing side of it gave us some real nightmares and some real challenges. And I'll just quickly kind of go through the ingredients that make up this machine. So the heart of the machine is the fuel cell. So where I said that the diesel machine would cost somewhere 120,000, 130,000 pounds, the fuel cell alone on this machine costs 98,700 pounds. And the reason for that is that it's full of platinum. Platinum's, I think, something like $1,000 per ounce at the moment. So there are not many ounces of platinum in there to get to that price. The other thing that people didn't really tell us when we started this was the demands on the cooling pack. So where with a traditional engine, the temperature can get up to about 100, 105 degrees Celsius, in a fuel cell it has to stay at exactly 60 degrees Celsius for the chemical reaction to occur effectively. What that means is that if you're working in an ambient temperature of 25, 30 degrees, the difference between your cooling temperature is for an engine, the difference is probably 70 degrees. For a fuel cell, the difference is probably only 20 or 30 degrees. So what that means is we need a much bigger radiator to dissipate the heat. And where unlike with a truck or a car or a bus, you've got airflow coming towards you all the time, these machines work in their own microclimate. So we had to put a large 12 kilowatt fan on this machine to just blow airflow through, which again takes power away from the fuel cell. The other thing that people didn't tell us about the cooling pack is what goes in it. So because the coolant goes straight through the middle of the fuel cell, and the fuel cell is this electrical device, the coolant can't conduct electricity. So we have to use deionized fluid. And when we first built this machine, coolant probably cost on a diesel machine, I don't know, £2 a litre, something like that. The engineers nicknamed the coolant on this machine whiskey because it cost the same price per litre as a bottle of whiskey. It was about £20 per litre when we built the machine. I think the price now is about £46 per litre, so a really good bottle of whiskey. But there's some other real challenges with that fluid because these machines, they lead a hard life. And they might start off life in the UK, but then they'll go off to other countries throughout the course of their lifetime. And the challenge we've got is that, things happen. Coolant pipes burst off. They might burst, they might pop off. What normally happens is somebody goes, gets a piece of duct tape, wraps it up, gets fluid, gets some water from wherever they can, fill up the coolant, and then just get it back to the yard. If you do that on this machine, you've scrapped your £98,700 fuel cell. Real challenge for how these machines work in the environment. And the other thing to say really is that we've also got batteries on this machine. So this machine essentially is an electric machine with a fuel cell range extender. But unlike with our mini excavator where we've got 20 kilowatt hours and they were £8,000, we've only got 5 kilowatt hours of batteries on this machine, but it cost us £32,000. And the reason for that is that these are lithium titanate power batteries. They're designed to take in energy, and I was talking about that 27-second dig cycle. It's got to take in that energy in half that time and then deplete it really, really quickly. The fuel cell can't do that. The fuel cell is sort of similar in some ways to a nuclear reactor. It likes to warm up gradually, it likes to stay steady, and then it ramps down at the end. But obviously, for our machines, we need that transient load. We need that high power, that grunt when you need it. So we've got to supplement it with batteries. So I've maybe put a little bit of a downer on fuel cells here. For our industry, this is based on our learning, we just don't think they're right. It is the most technologically advanced machine we've ever built. It's fantastic. We did talk to our chairman about whether we should strip it down for parts and do something else with it. But he said, no, let's keep it. Let's learn from it. Let's develop it. Our founder, Mr. JCB, had a good saying, don't complicate, simplicate. So that's what we're going to try and do. We're going to try and take the good bits off it and learn from it and develop it over time. But really our summary of it is that it's too complicated. It's not robust enough. The other thing I should say is that fuel cells, they don't like dirt and dust and fumes. It's sort of a hazard of the job for this kind of machine. And then finally, it's too expensive. So we think this machine would probably cost somewhere around the region of 3.5 times the price. What I haven't covered here is what the residual value of the machine is, which is currently unknown. And I think similarly to kind of the truck industry, our industry lives on residual value, on being able to change your assets quickly and knowing exactly how much your machine is worth at the end of its life. We just don't know with this machine, which is again another reason why we're going to keep running it. So back in the summer of 2020, we reached a crossroad. We presented to our chairman, Lord Bamford, our battery electric machines. They're great, fantastic for compact applications. We presented the hydrogen fuel cell, again, technologically the most capable and advanced machine we've ever built, also the most expensive and most complicated. It's not right for our industry. And so it was in the middle of COVID that we got together in one of those rare breaks between lockdowns, and really it was our chairman that said, well, why can't we think differently? Why can't we use the tools that we've got around us to do what we do today, but in a different way? And really that's the start of the hydrogen engine. So the first thing that we wanted to do was to emulate a fuel cell. What we like about the fuel cell is that you put a zero carbon fuel in, you put hydrogen in, you put air in, and you get steam and water out the tailpipe. We really like that, and we want to do the same with our engine. But the second thing is that it's got to match the existing technology. It's got to have the same power, the same torque, the same performance as the existing diesel engine today. We want to be able to take a diesel engine out and put a hydrogen engine in. We want to build hydrogen engines down the same assembly lines as our engine factory today and build hydrogen machines down the same assembly lines that we do today as well. And this is a really, really critical point because I think we were about 2 weeks into the project and our power systems engineering team came back and said, well, what do you want? You know, if you want efficiency, you can't have power. If you want power, you can't have same performance. We said, no, it's very clear. It's got to be exactly the same as the diesel. The operator can't know the difference. And that brings me on to my third point. So it has to have the same identical operator experience. The operator needs to be able to behave in the same way on the machine. It has to be similar refueling, familiar, quick. And then the servicing and maintenance also needs to be similar as well. I was talking to somebody earlier around our engine, and they pointed out that, you know, we have a fantastic experienced team of people that can develop, maintain and service existing fleets of vehicles. Are they going to have to reskill, or can we just apply those skills to a new technology? So that really brings me on to creating the hydrogen engine. And the first thing we did was we looked at 76 different technical papers. So people have looked at hydrogen engines in the past. The first time that people developed the hydrogen engine was in 1807. In fact, the first engine that ran on a car was powered by hydrogen. But for one reason or another, liquid fuels came in and the technology was put on the back burner. Then towards the late 1990s and early 2000s, people started getting interested in hydrogen combustion again. So you can see up here, we've got, on the top right, we've got our BMW hydrogen car. And what we found was that people, through these studies, we learned that people effectively had taken a petrol engine of the day and they'd put hydrogen in. And they ran, but they didn't work very well. They were, and bear in mind that an engine from the 1990s, there was a 7-litre V6, 6-litre V12, they weren't very efficient anyway, naturally aspirated. You put hydrogen in, they're not very efficient either. So what we realized really from all these papers was that we need to go back to basics. We need to understand exactly how to design an engine for hydrogen. And that's really, really important. The way we kind of think about it today is that if you only had petrol engines in the world and you developed a fuel called diesel, you wouldn't expect to put diesel in a petrol engine and for it to run very well. You've got to design a diesel engine. So in just the same way, you've got to design a hydrogen engine for hydrogen, taking into account the really unique characteristics of hydrogen. So we then broke that technical challenge down into 11 key technical issues and then really summarized it into 4. The first one really is the mixing. So where with a liquid fuel, it's been relatively straightforward for years. If you've got a water pistol, you can shoot it, you know where the water's going to go. With a gas, it's like me trying to breathe and get it out the door at the back. Really, really difficult. But fortunately, in the past 20 years, we've also had major advances in computing technology. So we've now got cloud computing, hypercomputing, which means that we can do computational fluid dynamics simulations overnight. Where before we would have had to design and develop and build a physical engine, test it, see what worked, what didn't work. Now we can do that virtually to really understand it. So the team's done something like 160 or 170 simulation runs now of this hydrogen combustion mixing with the air in the cylinder. The other thing to say really is that where for years we've developed diesel engines that work at very high temperatures and very high pressures, we're working at very low temperatures and low pressures with this engine. What we want is a lot of air and not very much hydrogen. We want to be extremely lean, which you can't do with petrol and diesel, but you can do with hydrogen. So that brings me on to the air compression. So JCB engines have had turbochargers on for decades. But the other difference between 20 years ago and now is that where 20 years ago a passenger car would have probably been naturally aspirated, relatively large engine. Now cars are running on very small engines with turbochargers, such is the power of turbocharging technology. So we're really using that turbocharging technology and optimizing it to run with a hydrogen engine. We've got to put in significantly more air into this engine than we do with our diesel. So originally we started with a big turbocharger. We thought we needed one the size of a dustbin. And then we ended up actually, we've gone to a very small turbocharger that runs at 122,000 RPM to get all that airflow in, to cool down that combustion and create that perfect mixture. The next advancement was spark ignition. So not new to the world, but it was new to JCB. So for years we've worked on diesel engines with compression ignition. Now we need spark ignition. And when we first put our spark plugs into our cylinder, I think it's fair to say it was similar to kind of a lightning bolt that we put in. We realized that actually you need to back it off quite a lot. You only need a tiny spark to ignite hydrogen. The advantage of using spark plugs is that it gives you extra control as well, which is really good for the combustion process. And then finally, it's steam management. It's the water that comes out of the tailpipe. We've always had water in our tailpipe through regular diesel combustion, but now with hydrogen combustion, we've got a lot of water. So it's what you do with it. So originally we looked at, well, could you condense it? Could you, what can you do with it? But really now our exhaust is more like an air vent, like a kitchen air vent, trying to get that steam and that moisture away from the machine. The other challenge we had was the oil, the lubricating oil in the engine. And for years you don't want to mix water and oil. And so I think it was fairly split, half and half down the design office in our power systems team of, do you design an oil that repels the water, or do you design an oil which attracts the water? So to fix the stalemate, we recruited our company's first chemist, and she came in and she told us that actually no, you want an oil that attracts the water, that then as it gets up to temperature, it then boils the water out of it. Really interesting developments, unique to hydrogen engines that we've never really thought about with our diesel engines before. And so there you have it. This is our hydrogen engine. It gives you the same power, the same torque, but zero carbon, and importantly, zero compromise. We shouldn't expect our customers to compromise when they adopt decarbonized technologies, when they adopt zero carbon machines. I think that's one of the challenges that we've got going forward as machine and vehicle developers, is how do we make sure our customers always have something better and that we're not asking our customers to have something worse. I think that's really important. So we make engines, but we also make machines. And so really, the proof of the pudding is putting the engine in the machine. So this is our hydrogen-powered backhoe loader, which we built as one of our first prototypes. And just bear in mind what went into building that fuel cell excavator. Really, this backhoe loader is relatively simple. So this machine we built in 6 days. We gave our engineering team the engine on the Friday. By the following Thursday, the machine was up and running. It was simply a case of taking the diesel engine out, putting the hydrogen engine in, take the diesel tanks off the side, put hydrogen tanks on the side. Bit of pipe work, bit of software, and away you go. Such is the power of using a transferable known technology. So we've reinvented the technology. We've delivered a robust, reliable, and serviceable machine. So at the moment, we're now going through testing and development of our products. We've done something like 25,000 hours now worth of testing in our quarries up in the Peak District. We've done 25,000 miles on the road to prove to the Department for Transport that these are safe to go on the roads. So we're proving out that technology. We don't want to deliver a prototype to our customers. We want to deliver a complete solution that has a known life that can last for decades. And then finally, it's affordable and adoptable. So really, there's no rare earth elements in that engine. It's steel, iron, aluminium, rubber, normal materials. And as such, it's a similar price to the diesel engine today. Relatively transferable. Well, we've now got spark plugs. We've also taken off an expensive diesel fuel injection system. So actually, in terms of engine to engine, it's pretty much comparable, and certainly with production volumes, it'll be comparable in the next year or so. The challenge really comes down to hydrogen tanks, which are a premium, which are produced in sort of small volumes at the moment. But again, there are large investments by big companies to really ramp up those volumes and get the price down. So where with a battery machine, for a compact, it could be twice the price, up to a large excavator could be 4.5 times the price. For a fuel cell, it's probably about 3.5 times the price. We see our hydrogen machines delivered to customers at probably a 25 to 50% on cost to start with. But rapidly, we can see that getting down to cost neutrality. And that's really important, because actually, if we can deliver a product to our customers that doesn't cost any more, or not much more than a diesel machine today, if we can get the fuel for the right price, which is another topic entirely, but if we can get the fuel for the right price, and countries around the world are working on that right now, putting huge investments in, actually we can decarbonize and get to net zero much, much faster by using existing technologies that we know today, where we don't have to wait for future developments, but we can really tackle the problem right now. So I'm just going to leave you with a video and a message from our chairman, Lord Bamford, about this programme.
I'm often asked, why hydrogen? Where does the power come from? It comes from that. That is a glass of water, H2O. Is split the H2 from O, and it's possible to do it in scale and around the world.
This is power. The power to move the earth. The power to change the world. This is JCB's hydrogen combustion engine at work. Welcome to the future.
Meeting the UK's ambitious goal of cutting net carbon emissions to zero by 2050 takes a lot of bold thinking, a lot of hard work, a lot of innovation, the kind of thing JCB has been delivering for over 75 years. 2 years ago, almost to the day, I set the challenge that we should be making hydrogen engines for the construction industry and for agriculture. 2 years later, we have hydrogen engines working in the kind of equipment that JCB makes a solution that delivers power in the same way as conventional engines, but with none of the fossil fuels.
So where did it all begin?
Well, in the early days of the hydrogen story, we believed the only technology available to us was a fuel cell. So we got on, made a fuel cell prototype, 20-ton excavator. We started to understand the complex challenge of putting a fuel cell into a piece of construction equipment. Construction equipment machines need energy quickly, whereas fuel cells were maybe better suited to a more gentle environment. And we started to realize that maybe fuel cells weren't too good for response, were too complicated and too expensive for the market that they serve. We knew we at JCB could do better. The two machines we have on site are game-changing. Firstly, we've got a backhoe loader. Secondly, we've got a construction load haul. What we've done is we've taken our hydrogen combustion solution, we've incorporated it into both machines. We've then worked out how to remove the fossil fuel tank, replace that with hydrogen tanks, and now we've got both machines running. Same characteristics of speed, of loading, of digging, performing in the worksite.
So what's the secret? It's this.
This is not a conversion, this is brand new combustion technology. We've had to look at almost every facet of the engine and we've completely re-engineered it to run on hydrogen. It's a zero carbon fuel and it gives us a zero CO2 solution. We've kept the DNA of the engine. The components are familiar and common. The big difference is the fuel. We've gone to a zero CO2 hydrogen gas. We inject it into the engine. We've lowered the pressure, we've lowered the temperature, and that gives us a clean burn and a zero emission product. We've worked really hard on the performance characteristics of this engine. We've done that to make sure that we deliver exactly the same power and exactly the same torque as the diesel power plant that we've replaced.
But it's on refueling that the hydrogen combustion engine really comes into its own.
Most of our machines, 97% of them in fact, the fuel is delivered every day while the machine keeps working. So we've developed a fueling system, a hydrogen bowser, so we can take hydrogen from the tube trailer, decant it, and deliver that hydrogen fuel to the machines that are working on site.
These are more than prototypes. These are fully fledged machines. Working right here, right now at JCB, we're proving daily that hydrogen does work, that it's a clean, renewable, transportable fuel, capable of storing and delivering the power our industry needs, quickly and efficiently, without the carbon. We're working towards a hydrogen future with zero emissions. Surely that's a great benefit for the world.
JCB, always looking for a better way.
Hopefully you found that insightful and useful. Thank you for having us to present at the conference today. We really appreciate the opportunity. And really, I guess, if I could just give one ask of all of you listening is really think about the technology and ask people for the technology. If it's what you think you want for your industry, go and ask for it and create that demand pool. So thank you. Questions?
Wow,
Sorry.
Tom, I mean, that was amazing. I feel like we've had a proper lesson in engineering.
Not a lecture.
And I'm sure that's just, the start of things. Brilliant to share the journey that you've been on to get to where you are today. We have had some incredible questions from the audience as well, so I'm just going to crack on and get into it. First question is, when and why did JCB develop its sense of responsibility for the carbon footprint of its products bought by customers?
Sure, yeah. So nobody's asking us or telling us at the moment to get to carbon to net zero except by 2050. But really, as a private business, which is owned and run by Lord Bamford, I think he sees a responsibility to protect the business for future generations and have that broader view. I think as a family business, there's different things at play. It's not just ESG targets, but actually it's a genuine passion and desire to make the world a better place.
Yeah, I mean, it's incredible to take on that responsibility, and hopefully others will follow in his footsteps. Next question is, what sources of hydrogen do JCB endorse, and have you partnered with any providers?
Sure. So green hydrogen is what we love. So that's hydrogen made from renewables. I will say the machines, they don't care what colour it is, providing it's hydrogen. But really, it's really important that the demand, well, there's two sides of it, isn't it? We're always told that hydrogen is either chicken and egg. I don't know whether we've created the chicken or the egg, but we do need that hydrogen production to come online. I know other countries are putting a lot of money into creating renewable green hydrogen or using blue hydrogen, if that's what you want to do. But really, it's not our area of expertise, if you like, and really we need the fuel suppliers to really come to the party and work with it.
You obviously said that the hydrogen fuel cell just isn't, it's not the right time, it's too expensive, it doesn't work for you at the moment. Do you think there will be a time where it is cost effective? Mm-hmm.
I think never say never. Now, you may disagree having seen the presentation, but as a business we do stay technology neutral, and that's really important to us, and we also really promote that actually everybody should stay technology neutral, instead looking at the outcomes. So if there's a battery technology which can somehow be 40 times cheaper, can be charged in an instant, well, we'll absolutely look at it and reassess it. So I think you've always got to look at that. I think one of the challenges of the fuel cell world is that, I mean, it's doubly chicken and egg, because if nobody ever uses them, they'll never develop as a technology. And really, it's not a case of time, it's a case of sort of production volume. And if you think that the engine's had probably, 2 centuries worth of development on, the fuel cell's got a long way to catch up. If it is at all. But we remain technology neutral and open to it, and we're going to keep researching it, and if something comes out, we will use it.
So you remain partially committed to potentially developing fuel cell technology as well.
Something like that, yeah.
Great. You haven't given up on it completely.
No.
Does the tank hold liquid hydrogen or gas?
So it's gaseous on our machines, so we can get enough hydrogen on board to do a full day shift, which is really important for our industry. So we want to refuel once a day. So we've worked really hard to kind of work with the efficiency to reduce the amount of hydrogen you need so that we can do gas. I know some people are looking at liquid in other countries. I don't think we've got any in the UK. We're certainly interested in liquid hydrogen for the benefits of being able to store more on board. But again, I think that's a little bit way out. We can start with gaseous hydrogen now.
I think the next question comes to someone that was obviously paying attention this morning, that 60% of collisions are caused by the driver, because the next question is, how safe is a vehicle with hydrogen fuel tanks if there's a collision? Yeah,
so we'd heard all of the hydrogen bomb, the Hindenburg, and all these kind of things when we started. What we're actually quite surprised at is how strictly controlled hydrogen is. So hydrogen's been used in the oil and gas industry for decades, and actually the safety standards are so much higher than they are for petrol and diesel. You think about your petrol and diesel car, and when you fill up at the petrol station, really it's kind of crazy when you think about it in terms of being able to slosh around this liquid fuel. With hydrogen, you won't even, hopefully you'll never encounter it and you'll never see it. It's a completely sealed system. So you can't get it on your trousers, you can't get it on your hands. So the other thing is that on the hydrogen tanks on the sides, our machines, people often say, well, aren't they a bit vulnerable on the side? So we've done lots of testing, and we've got a couple of quarries, so we can do all sorts of fun things. So we've got this big metal torpedo, for want of a better word, which we dropped onto these tanks. And what we found is that they just bounced straight off. These tanks are designed to be, I think they're bullet tested, they're chemical tested, all sorts. So no concerns with hydrogen safety here.
Good. And finally, are NOx created as a byproduct of the hydrogen combustion process?
So really that's kind of, air quality has always been one of the I'd say challenges of hydrogen. I think it's a reputational challenge more than anything. At JCB, we've been working on air quality for the past 2 decades. Our stage 5 engines, our diesel ones, are so clean now. And actually, before we kind of got into the whole net zero strategy, we were working on how do we make our diesel engines zero emissions. We had our zero emission diesel program. One really great advantage of hydrogen is that actually we can solve that problem in the cylinder. So where with diesel we were at high temperature, high pressure combustion, we're now at very low temperature, low pressure combustion. And we were always told in our engineering training that you always produce NOx when you burn things. Well, that's not actually true. There's a certain temperature above which you start making a lot of NOx. So actually, if you can keep to those low temperature combustion, you actually take the problem away in the cylinder. And we're seeing some fantastic results that we've had independently verified by 4 different global certification agencies, really to kind of just prove that this is a clean technology. That, you know, we're not going to develop a product which is a challenge for air quality and efficiency. You know, these machines are going to be highly efficient and they're going to produce clean air.
Mm-hmm. Brilliant, brilliant. And actually, finally, just a quick one. I think you probably covered it, but just for clarifying with the audience, would this technology work in a regular truck?
So, yes, you may have seen.
Yes, but no.
So our chairman, Lord Bamford, likes to experiment with things, and we happen to have a 7.5-ton truck in our fleet, which was going to go into an auction. So we pulled it out of the auction and we put a hydrogen engine in it. And it does work, and it works fantastically well. It's not really our area of expertise. I should also say we put it in a Mercedes Atego van, and then a truck, and then we put it in a Mercedes Sprinter van. We haven't got anything against Mercedes. It's just what we had around us. But really, it's just to prove that the technology is scalable and transferable to those different industries. Mm-hmm. It's not our area of expertise. We're staying in the yellow stuff. But certainly there is potentially a future in other industries as well.
Oh, well, this is a nice question that's just come in. Not a question, but a comment. This is the most inspirational presentation I've seen today, and I would completely agree with that.
Thank you very much.
I think that's a perfect moment to end it there. Tom, it really has been an absolute pleasure. Eye-opening, I think, for everybody here, and we wish you all the very best in the journey. We look forward to seeing what happens next.
Great, thank you very much.
Thank you very much. Huge round of applause for Tom and Tom.